let's get rolling today. Mason and I, our mindfulness was talking about.
Yeah, sorry guys. I didn't mean to take
No,
any
it's
more
okay.
minutes away.
I'm supposed to be the one keeping control here, you know. So it was fun. It was good to chat with you, my friend. I do not have the exams graded yet. I've not even started. I haven't even looked at them. I haven't had no time. But Monday for sure. I'm gonna give a chance to do corrections on them. So if you're worried that things went bad on any part of it, you'll get a chance to correct things. I'm not here to be brutal. I just want everybody to kind of have a sense of math when you leave here. If we have that, then we're good. But we actually are starting some fun stuff today. So there is going to be a new WebWork opening up. Not WebWork, excuse me, My Open Math. WebWorks, our other system. So there's going to be a new My Open Math, and that'll probably open around 10 today, and we might, I'm hoping we have a chance to just start on it together. I think it's due next Tuesday. It's a small one, but it's dense. This is new stuff for a lot of us. Who's had calc? Somebody had calc in here before, right? Or not?
Probably Jack.
It was probably Jack. Was it Jack? Was anybody else had calculus? Cool. Oh, this is exciting, outstanding. I get to be the one to show you this stuff. Oh my God. So due next Monday. Tuesday. Tuesday, I got Tuesday. So that we can chat about it on Monday. Cool, so I got a story to tell. Anybody have dogs? What kind of dogs?
German Shorthairs and a German Shepherd.
What's a German Shorthair?
What is it?
Yeah, I mean it's a dog, but.
Yeah, it's like a medium size. They are hunting dogs. They're like a retriever dog kind of.
Oh, okay.
Yeah, very short.
That's a lot of dogs.
Kind of small.
3 big dogs.
We have a lot of big dogs.
That's big dogs.
We find a lot though.
Any dogs?
Yorkie Shih Tzu mix.
Yorkie Shih Tzu
Yeah,
mix.
so very small.
Very small, very Shih Tzu-ish.
Yeah.
Yeah. yeah.
Golden retrievers.
How many? What? That's
2.
plural. 2.
Mhm.
Oh, beautiful. Are they related?
No.
No.
I have a Rottweiler and a Shiba Inu.
Oh, you got tough dogs.
The Shiba's not.
Shiba's not.
And
Okay.
the Rottweiler just pretends to be. He has his own little teddy bear.
He's a big baby.
Yeah, he is
Oh,
a big
okay.
baby.
Oh. But he's like,
Yeah,
3 feet.
he's pretty big.
yeah.
I don't have any dogs, but I take co-partnership of Rory, Addison's dog.
Okay. Cool.
It's like my little son or daughter.
Yeah. I've got 2. I've had up to 3, but we're a pug family. I was gonna get some pictures, but I'll have to get them later. I didn't have time for that. So what I wanted to imagine is a dog race consisting of 3 pugs. I only have 2. I'd have to bring another one back from the dead or something like that to get 3. But let's imagine a race between 3 pugs. So it's a slow race. This is not a fast race. It's possibly a distracted race. And I want to show you how they each did in the race with 3 separate graphs. So the race is a 100-foot race, which for a human would be not much. For a pug, it's a substantial distance to travel. So that's 100 feet. So this is distance traveled. And then down here, we're gonna have time in seconds. Same thing for all of these. So we're gonna have distance traveled. 100 is the thing I'm marking off. And that's gonna be the same here, so distance. And we can call this, just if we're gonna get a little fancier, D of T. D of T. D of T. And our time units are seconds in all of these. Cool. So I've got three very different behaviors, and I want to put them up here, and then I want us to think about them a little bit. So the first pug travels, the distance graph looks like this. And out here, this is 30 seconds. So this is, if we were keeping track of the distance, just watching the distance toward the goal that the pugs travel, this is measured from the start line. And it is their current distance from the start line. So pug 2 had something a little bit different, and I'll get some units on these in just a second. I want these all to end at 30 seconds and 100 feet. And then this last pug, kind of a weirdo, little bit of a weirdo, but I'm not going to say in what way yet. Rocket. And so then this, I want that to be right at 100, and that is 30. Okay, cool. So 3 very different critters running this race. Let's mark off some units. So let's see, this is about 15 here. So let's say 10, and I'm gonna cheese that out and say that's 5, even though it looks like 4. This one, let's see, so 15 is right there, 10. And these worked out a little bit better. Again, cheesing, that's probably 6. And let's say that that's like 17, and then 30. And then this last one, let's see, so that actually, I'm gonna try to be less cheesy and say that's 7. That is 15. And then we gotta get some horizontal units too. This one here, and this one here, this will be 25, this will be 20. You know, again, some cheesiness occurring. So then this would be about 60 feet. This would be about 110 feet. And I think I got the important parts there. On this one, this looks like 20. And then we'll just kind of leave it from there. And up here, this looks like maybe 60. This one here looks like 40. And I think we're good. Cool. So let's get these graphs into our brains. So what I would like you to do, just spend a few minutes. What is the movie of each pug? So you took a video of these pugs traveling. What is that? What does it look like? So you're on the sideline. Here's the race. Here's the start. Here's the finish. For pug 1, 2, and 3, could you just take a few minutes and write out what you would witness if you're watching a movie of this little potato creature running toward the goal, or maybe other directions? I could use the restroom. I'll be right back. sorry, I didn't mean to frighten you. If I know, I won't ever do that again. So Nadia, what we're doing here is we have 3 pugs in a race. This is the distance they traveled with respect to time. And we're just trying to come up with a movie of what it looked like to watch each pug from the side. I tried to make this as realistic as possible. I looked at pug speeds and did some conversions and stuff. What you thinking?
I think that it was going to stop at this point because it's not.
Cool. Yeah. So what about the so yeah? Can you? What's the movie then for this guy?
That's what I'm.
So you're still
Yeah,
thinking,
yeah.
but that's a good observation. That's 100% correct. I'm just curious how you're making your movies notes.
Not Quentin Tarantino.
That's good. There should only be one of him.
Probably.
I think
Ooh.
the friend is the dog is to the line. And then I go for it, like when he was for each second, how long seconds.
Oh, that's cool.
That is,
Oh, I like that. That's neat. That's a very cool way to break it down. Yeah. Is that a little pug? What is that?
Yeah.
Is that a little potato
I didn't
dog?
want to get too artistic, even though I could, obviously, but I didn't.
Feel free, you know. We're all friends here. It's good. No one will force you to share your artwork. Worse than having to share math. Have y'all seen on TikTok the couples painting each other, like married couples?
Oh yeah.
Yeah. I probably get it because I'm like an old guy on
I mean,
TikTok. so.
it used to be on like, did y'all ever watch Practical Jokers?
Yeah.
They used to do those, but like make really shitty like pictures of like their significant others and like piss other like random people off. Just a.
Yeah, no, it's good. It's pretty damn funny.
It is pretty funny.
Yeah. Let me give everybody a couple more minutes. And maybe can ask some questions over here. So what do they have in common? What aspects of this are in common to some questions to consider beyond our movie itself, but 0, here's the thing we're kind of working on. There's a little vagueness to the questions too, just to promote different. Do you have answers? You do at least pretend.
I do.
That's awesome. No, it's cool. You don't have to pretend like you're writing. That's cool. That's awesome. Oh, I don't want to let Lorelei finish up her analysis there. So maybe some other questions too. you mind working with me for a little bit here?
Sure, I'll be the test
In a
dummy.
thank you, my friend. And I won't just harass you today.
Okay.
Don't worry, you're
No,
just
for
the
sure.
first one to
No,
be
I-
harassed.
Don't even worry about it.
I'm not really.
Yeah, so like my mindset was
Yeah.
that from 5 to 10, there's no increase in distance.
Okay. So how does he start off? So
Starts
like,
off.
here's the bell.
Well, he starts off going from 0 to 5, or 0 to 20, I guess.
0 to 20 feet in the first 5
5
seconds.
seconds.
Cool.
And then from 5 to 10 seconds, it's at a standstill.
Just kind of stops.
Yeah, it's also a squirrel or something.
He absolutely got confused.
Yeah.
Yeah, tired.
And then remembered why it was there, and then proceeded to haul ass for 30 seconds, or for another 20 seconds.
Yeah, exactly. Does that sound? Do we all see that movie happening here? That's great. Yeah, beautiful, beautiful. What about this one here? Lorelai, did you finish?
Yeah. So from 0 to 5 seconds, it didn't move at all.
I didn't hear the bell,
It just
right,
kinda
or
stood
something.
there?
Yeah, it just kind of stood there. Yeah.
And then from 5 seconds until the 10-second mark, it ran until it got to 60 feet.
Hell, it did like really
Yeah.
cooked.
Good
Holy shit.
sprint.
Yeah, big sprint, and then.
And then wore itself out with that and paused for another.
You got the
we'll
story.
say until 15.
Yeah.
And then got backtracked.
yeah, kind of
back
lost
until-
some of the
yeah.
distance. Yeah, kind of stumbled back or something.
And then in the last couple seconds, just zoomed up to that 100.
Got a little pat on the butt.
Yeah.
Got the right
Yeah, that's the
direction.
direction you gotta go in.
Exactly. That's a beautiful story. Yeah. Does this sound good? Did everybody see that story? Katya, do you feel like you came in a little late? I don't know if you're feeling like telling
Yeah, I
this
can do
story.
it.
Okay, thank you.
So from 0 to 7 seconds, the first 7 seconds, he like sped up to 60 feet.
Yeah.
Kind of like the one before. And then the same as the one before, they kind of like looked at each other and were like, what's happening?
That's right. That's
and
a
took
lot.
break together.
Yeah, that's a lot for a pug to do.
Yeah.
So totally
They were
tired.
kind of confused. And then from 15 to 20 seconds, he also realized what was happening and kind of decided he wanted to win. And then took another little mini break because he got tired. And then kind of went back a little bit because he missed the ending mark. And he had to go back.
What did he actually do at the end? So he's running, and that's the goal point, right? What did he
Yeah.
actually do?
He passed it.
He kind of ran past it,
Yeah.
and then paused.
Yeah. They
Was
had
like,
to
what the
lead
hell?
him
Exactly. Then had to
he
go.
had
Yes,
to
they
be-
had to be guided back. So this one actually won the race, right? It actually got to the goal of 100 feet in the shortest amount of time. I don't know, what does that look like there?
17, 18.
Yeah, 17. Yeah, so we'll go over 18 just so we don't have to put halves and stuff in there. So Pug 3, this is 1, 2, 3. We can come over here. Pug 3 won by completing the race. And I don't know, there might be rules that you have to actually know where the end of the race is to win. If you keep running, people start to question your mental state, but these are pugs.
I think I have an answer for this.
Okay, yeah, hold on, let me get this. Cool. Won by completing the race in, 18 seconds? Pretty amazing with a break in there as well. Yeah, what were you gonna say, Mason?
I was gonna say I can, so pig number, or sorry,
Pigs.
Sorry,
They're like little pigs in
yeah,
many ways.
Lucky pigs. No, the pug that traveled the fastest was number 2.
Number 2. So could you explain what you mean
So
by
he
that?
traveled the largest amount of distance in the shortest amount of time.
Beautiful. Where are we?
So
looking?
from 5 to 10 seconds, he traveled 60 feet.
Yeah, awesome. Can we see that? Yeah.
Velocity would just be the distance divided by the time it took.
Oh, you're answering all sorts of questions.
Yeah, this part I do remember. this.
Oh, this is great. This is fantastic. Yeah, Hannah.
Would 3 be faster though, because from 60 to 100, he traveled
That is
40
true,
feet
yeah.
in 3 seconds.
Oh,
So the second.
That is true. Technically,
I'm sorry, where are we looking?
Sorry, the
Pug
pug
3.
3, and from 15 to 18, You
That
want
is,
40
it's like,
and
it's
30.
slightly bigger.
Oh.
So it's like.
It's slightly bigger.
Okay, yeah, let's get those computations on the board. Let's take what May said about velocity. So velocity is, what did you say, Mace?
Distance divided by the time.
Yeah, so is distance divided by time. I want to introduce some symbols that'll become really important to us. In particular, velocity can be thought of as the change. So this symbol here is a capital Greek delta. It's the D, one of the original D's. This is the capital delta. This is a lowercase delta. It looks more like our little d. So this delta signifies change. And it's really what calculus is all about. The change in distance divided by the change in time. And that's the computation we're going to use to think about number 2. So let's actually do these comparisons. So good eye on that one, Hannah. Thank you.
It should be, the number 2 should be 12, because it'd be 40, right?
Mhm.
Or-
I'm sorry, okay, so let me come here. Number 2, and where are we
Or
looking?
60.
60 divided by 5.
60 for 2, and then divided by 5, so that'd be 12.
12.
Got it. Yeah, so let's make some little notes on this chart. So here, the velocity, and these look like straight lines, is equal to 60 divided by 5, so 12.
Yeah.
12 what?
Feet per second.
Feet per second. So whatever the top units are, divided by the bottom units. Yeah, feet per second. Cool, that's super fast. That is,
Yeah, he was hauling.
yeah, that's like 8 miles per hour. I made some little conversion notes on my,
For a pug, that's hauling.
that's insane. That's for a person, 8 miles an hour.
That pug is juiced.
That body is absolutely juiced. Yeah, this was like just taking some caffeine here and just like a little some caffeine treats.
Little epinephrine.
Absolutely, yeah. And then down here, this was the band that you were talking about, Hannah.
Yeah, so
That, yeah. So what do we
40
got?
over 3, and that'd be like 13.33.
So 40 over 3, and that is what? Did you crank that?
It's like 13.3 repeated.
13.3
think.
feet per second.
Yeah, oh, so
Cool. No, that's cool. That's cool. And then what was this one? This one's a little sus here. What was this?
The 60 divided by 7.
60 divided by 7, which is not even 10.
No.
So,
8.57.
oh, thank you. 8.57 feet per second. Yeah, very nice. If I were to take this one here and grab a different section, so we have this velocity, and actually, let me back up. The velocity we're figuring is computed by taking 2 endpoints, finding the change in their height divided by the change in their distance. So what we could have here, I just want to put this up. This is distance at the end minus distance at the start over start time end minus time start. And this is not just velocity, it's got a more specific term. So it makes you absolutely right. Velocity is a measure of how distance is changing with respect to time, but since we're taking 2 endpoints, this is actually the average velocity.
I was gonna make that because it was just like the change in distance over the change in time would definitely be more closer to average.
Yeah, beautiful. Yeah, so your mind is absolutely in the
I
right place.
don't remember if I knew this from my math classes or my physics classes that I took.
Little of column A, little of column
Yeah,
B,
column B.
probably. It's very physicsy stuff going on here. So average velocity is, what is the average velocity for all of them, for the whole race? So let's take a look at that. Because the answer to question 1 is related to that. So what is the average velocity for each over the whole race? So for this guy, what's the average velocity for the entire race? So from here to here.
Wouldn't they all just be 3.33?
Yeah.
They're all the same. Yeah, exactly. So for this one here, it's going to be the 100, and we could say we started at 0 just to keep that rhythm going over 30 seconds minus our start time. So that is, yeah, 3.33 feet per second. That is the slope of this line. So notice that that average rate of change, that average velocity, is the slope of the line that connects the two endpoints. Does that make sense? It's just the change in height over the change in run. Each of these has that exact same slope between the start and the end. So here, the average velocity is going to be, again, 100 over 30 and 3.33 feet per second. Same thing right down here. Average velocity is 3.33 feet per second. But that doesn't really tell much about the story. I'm sorry, what did I?
I was just thinking out loud, sorry.
Oh, what were you thinking? That's cool.
I was just gonna say you take all of them together, divided by 3 to get average.
Oh, so you were like taking them, you were averaging,
Yeah.
finding the average of all the average
Yeah.
velocities. Yeah, cool. And they would all be right smack on
One, like whatever.
3.33,
Yeah.
right? Because they're all the same number. We add them up. Yeah, nice. I like that you're cranking ahead and just your mind is. You know that there's that meme where there's the woman looking at all the equations. Do you know the one I'm talking about? That's what I'm picturing right now. I'll find it and show it to you.
Put it on my laptop.
It's from some TV show, I don't know where. But that's just a very coarse description of these races. Because there was a whole lot of detail. There was much more interesting things going on than this. So what would be a better way? What would be a better way to describe, because this guy won, right? Which guy won? This guy won, actually. So we'd have to decide if this matters or not. If it didn't, what would this guy's average velocity be? So if everybody was like, you know what?
He made it.
He made it, that's cool, he's a pug, for God's sake. He was all jacked up on epinephrine. Especially this guy at the beginning, right? Totally highly caffeinated. So in just this little window from 0 to 18 seconds, what was this guy's average velocity? 5.55. Ooh, that's, wow, you're cranking the stuff, you're cranking fast. Nice, that sounds right. So you took, how did you do that one, Hannah?
Just 100 divided by 18.
100, the change in distance
Yeah.
over 18 seconds. Yeah, you got 5.55.
5.5 repeated.
Cool. So we'll go 5.6 just because that's repeated. So this guy was really cooking, really won the race, definitely had the, oh, I just realized you're icing your shoulder.
I'm a broken person, guys.
Oh, no, I'm sorry. I didn't mean to bring attention.
That's okay.
Yeah. So what's in common is that average velocity between 0 to 30 seconds. That is something that is in common. We know which pug traveled fastest, and we had to actually, so this question might have a couple of different answers, right? Which pug traveled fastest at some point during the race was it this guy here? Yeah, so pug 3 had the fastest burst in the race, but overall, this guy probably, where was finished early guy? This guy probably traveled the fastest and then kind of just screwed up the race by not knowing when to stop. Pug 3 won, we already know that. What is velocity? Mace gave us that and also gave us average velocity. So let me ask kind of a more open question here. If you were describing how would you describe these things to people? What would be the best way to describe what we're witnessing here? And it might be that these things are the best way.
In terms of like vocally? Like,
Vocally, yeah. Would it be a simple matter?
Not necessarily.
I don't think so, right? Because you kind of need to describe all the different behaviors. Like, think about the stories we told at the beginning. Those were pretty complicated. They were actually much more amusing than looking at the graphs. Let's look at a couple other things here. Notice how, let's just take one of these straight line segments. So in this straight line segment, the slope of that segment was 8.57. That's a straight line. What if I took it and right in the middle here at 3.5 and 30? Can you see that I have the same average velocity over that little interval?
Should part of the same one.
Should be the same, right? Because the slope is what I'm measuring here. So the average velocity in this little window is going to be 30 over 3.5. And if we crank that through, I'll try to get it before Hannah gets it. But I think that should be 8.57 as well. So knowing this rate of change here, this average rate of change, we kind of know everything about this whole pug's journey in at least that little segment or any of these straight line segments. The whole represents smaller bits of the pieces. But I want to come back to this one. What is going on between, let's get rid of this, 10 and 30 seconds on this one? And I made this one deliberately not straight. So what is actually happening here? Did you want to say something, Mace? Because it kind of looked like it.
Yeah, no, I was just gonna answer.
Yeah.
Is like rate of velocity isn't constant to that point.
I'm sorry.
His
say that.
velocity isn't constant.
Isn't constant at all. Yeah, definitely. In fact, what is his velocity doing?
It's slowing down, actually.
Slowing down because he's traveling less distance over the same units of time. So let's actually take a look at this piece and break it down and understand it a little bit better. So let's see. So we'll say that's 20, and then that's 25. Then I'm going to come up here and try to estimate that. So maybe that's 50. Maybe that's 75. That's not bad. And then maybe this one here is like, what do you think? Halfway between 90. What do you think there? That's 25 between those at 12. 87. We'll say 90. Like so. So we can actually come to this one, and instead of saying, oh, the average velocity here for this pug was 20, so change in distance over the change in time, that's a delta. For this little interval here, over, I'm gonna be really precise, 10 to 30 seconds is going to equal the change in distance, which is what, 80 feet divided by 20 seconds. And that is 4 feet per second. But as Mace was telling us, that's not the whole story. That's the average over this whole part of the journey. But that journey actually has a lot of change in it. The velocity is actually never constant in there. So let's take a look at just the intervals here. So let's do average velocity over these. Could you actually help me out here? Could you find the average velocity in each of these windows? So what is the average velocity in each window? I guess we have 4 windows. And I'll work on it.
with you. But it definitely beats just listen to me keep blabbing.
This guy here is 7. What is in that window? I feel like my lines aren't all. Something's a little weird, isn't it?
I think it's just like human error, to be honest.
I think, yeah, this one, they're just so damn. So let's make that one 95. Right there. Sorry, that's pretty. That's some shitty graphing. Like that. Okay, so then in this window, what do we got? We're gonna go from 95 to 90. And I'm missing one. So here's 75.
Are you at the 90 to 75?
Yeah, I think yes. But I'm not sure where the hell that 75 syncs up to now.
75 goes to 15? Or no?
No.
20, wait.
Right?
Yeah.
I think something's a little weird here. Yeah, something's a little foul here. So let's just actually, I don't even think that actually plays a role anymore. I think I got a little excited with marking off units. So 50, the next one is this 90, right? This is because I'm just looking at these little windows where they start and end. So in this window, it was 90 minus 50. How did I get the 75? Hold on, sorry folks. All right, so the average velocity here, oh, okay, that's what I was doing. I was just not reading correctly. So it's 90 minus 50 over 20 minus 15. Yeah, I don't blame you. I blame you too. That's 8 feet per second. Am I doing these computations right? Because
Yeah, that's right. But
It's-
then after 90, just go up to 100, or is there a number in between the 100?
there was a 95 that was
95.
supposed to be right there.
Okay.
And so that was this little interval here. So in that interval, it was 95 minus 90 over 25 minus
Yeah.
20, yeah. So 5 over 5 is 1 foot per second. It's super slow, going very slow. And then for the final little interval here, the average velocity, I think it's the same, isn't
Yeah,
it?
it's the same.
Yeah, so it's 100 minus 95 over 30 minus 25, so that is also 1 foot per second. I guess the point I want to make here, and I'm going to just make it, and then we can move on, is that we can compute the average velocity in a lot of different ways. And each one of them represents a different part of the journey, and it just kind of depends on what we're interested in. But keep it, the thing to take out of this is average velocity can be deceiving. And, oh God, I before E, okay. Very first time I applied for jobs after I graduated, I was an idiot in a lot of ways, just so many ways. But one of them was the cover letter I was sending. I misspelled received in all my cover letters. And I still can't get I before E, except after C right, but I have to say it out loud every single time. So friends, could we take a look in the problem sets that we have? And And I just wanted to do somebody else's graphs, for God's sakes. This is on page 77 of the book, section 2.1. So you'll have to go to the next chapter if you've got separate chapters. And if we could just look at problem 7. That's actually page 78. Could we please look at that together? And just, could you take a few minutes to work that one through on your own? This is page 78, verse 7. Things are going to get a little weirder. So we're looking at problem 7 on page 78 right now. Part C will be where it'll take some thinking, and we might not all do it the same way. Yes, sir. Yeah, go ahead.
For the last point, because the point ends at 30, and if we don't have any assumption that he moves or that thing moves after that point at 30 seconds, isn't he technically still?
Yeah, so I think we can just assume
Say
it
0.
stopped. Yeah, not 0.
I mean, the only reason, the only thought process in that is like from that point on, that there's movement in the graph up until that point.
Yeah.
So are we just assuming that like you just like phased out of existence? Like you just
Yes,
ran too fast.
Yes, that. Just
Okay.
totally hit a vortex in
Black hole swallowed
Sedona.
him.
Yeah, it was in Sedona, got picked up by a UFO. Absolutely. Yeah, it's just life ends right
Yeah,
here.
gotcha.
Yeah.
Cool.
Even just driving, right?
Just
Totally.
road ends.
Backing up, I guess, actually. That's what was the problem, the back up
yeah,
into
yeah,
the
no,
black
that'll do it.
hole.
Mhm.
Yeah.
Gotta watch the reverse camera.
Yeah, so let's see. So there's a black hole there. Looks like a Friday. Okay. Cool.
Cool.
Yeah, good. Does that help you answer the questions?
A little bit, I suppose. I guess it just means the answer's not zero, so I guess that does help.
So what could we do? I like the way you're thinking. So you're trying to figure average velocity here.
Yeah, because I'm on the question C about how fast was the car traveling at 10 seconds, how fast was it traveling at 20 seconds, how fast was it traveling at 30.
Yes. Yeah. Cool. I'm gonna come back to you. Let's
Okay.
check in. That's good, but yeah, I'll come back to you. Does anybody have our average velocity on the first 20 seconds?
Wait, first 20?
Or 0 to 20, isn't that right? Or did I misread the question?
Oh,
Yes.
sorry. A.
No, that's okay. Okay, cool.
Yes, that should be 15 feet per second, I think.
15 feet per second, are we agreeing on that? Yeah, thumbs up? Yep, okay, cool. So this was 15 feet per second. Got the change in distance, which was, what was that, 300 divided by 20? Yep, cool. How about here, could someone else tell me?
10 feet per second?
10 feet per second. And that is on the 10 to 30. Do we have five?
I got-
I have -5.
I had 6.6 repeating.
Well, let's talk. This is fun. All right, democracy.
You're all wrong.
No, I actually think Katya's got
I was-
it. It's a,
And her.
oh, did you?
Yeah, we both got -5.
You said -5. Awesome, Lisa. Cool. So check this out, and let's figure out what happened here. So from 10 to 30, we're in this window here. So we're going to take the distance at. Let's talk about how to do this a couple different ways. So distance at end minus distance at start over time end minus time start. And I'm thinking that some of the positive answers might have come because you were subtracting in a different order. Possibly also looking at the wrong point up there. But the distance at the end is 100 feet. The distance at the start was, I'm sorry, where was it? This was this guy here, right? So 10 seconds was 200 feet. So it's 100 minus 200 feet. And sometimes that will be negative if you were backing up. So the net change was an actual reversal, losing some distance. And then we had 30 seconds for that guy, and then what, 10 here? Minus 10. And so we'll get -100 over 20, and that is a -5 feet per second. So overall, losing distance on average over that, even though there was a lot of distance gained in the middle. That's why this can be misleading in some ways.
Understood.
So what, anybody care to talk about maybe what mistakes got made? Because that might help others.
Just remembering it's distance at like the two points basically. Just say.
I got it. Yeah,
It's like-
subtracting in the wrong order.
If you, like
Yeah,
for the
yeah.
first question, we could do it easily just by doing what was it, fucking 300 divided by 20 or whatever
Yeah.
for the average velocity. And that one's easy to get because you don't have to plug in the second point. You can just take the top distance divided by the amount of time. But for this one, you just have to do 2 points.
Yeah, exactly. And so you could actually do this in the wrong order. Just do it in the wrong order on the top and bottom. So the key thing here, the point I want to make is when you're doing these averages, these average changes, just have consistency from the top to the bottom. Because notice that if I do this backwards, because you were like 200's more than 100, so you probably wanted to do this. That's totally cool. So we could do that, but then these have to be paired perfectly with this. So I could do this, and now I've still got a negative. At some point I got to deal with a negative in here. No matter how I try to avoid it, I still get negative feet, 5 feet per second. So consistency on the top and bottom, that's the lesson from that one. All right, so then let's get to the more interesting one, C. About how fast was the car traveling here? Anybody care to help me out with this? Caroline, are you interested in stepping in here? Okay,
I don't think so.
that's cool. That's cool.
I got 20 feet per second.
Cool. And so what was your thought process here?
The velocity, just not the change.
Yeah, I'm sorry, so what?
Like, I did velocity, just not with the 2 points, like just
She
with
did the
that
first
single point.
Yeah.
Oh, so how did you do it with a single point? That's interesting.
200 divided by
Oh, so you took that over that. Oh, okay. That worked out, but only because it's actually the slope of this line here. I think, so in general, we need to have 2 points to get that average rate of change. So what you could do, so I like how you're thinking. What we could do is figure out approximately on either side of it, maybe, or we could say that the average velocity leading up to here, because there's a change here, right? It suddenly speeds up. So there's this velocity and then there's this velocity. And it's kind of like which one, and that was probably what drew you to, I want to just get that point in the middle. But to do an average, we need 2 locations. We will next week move into being able to do it at a point, but it takes some calculus to do that. So what we could do, and I like the way you're thinking about this, is I could grab a point near here and a point on the other side, really close to that location, and figure out that slope right there. I'm gonna put a little right angle there. So I could choose a point close to this on either side and then do the average. Or I could do what effectively you did, Katya, which was figure out this average velocity looks like it's pretty consistent here. And notice that you actually did find the average velocity over this first part because you took 200 minus 0, even if you weren't doing that in your head or on your paper, over 10 minus 0. And then that gives you the 20 feet per second there. So that was good thinking. It's like, what else can you do? And I'm really glad you said that. So with average rate of change, always get yourself 2 points. Awesome. Thank you, thank you. So then what about at 20 seconds? Up here at 20 seconds. Again, 2 different behaviors, not even straight lines. What could we do here to estimate the average velocity? What would you do? And there's not just one right answer. Yeah.
I did a little different. I calculated both, like from before, from 15 to 20 seconds, that velocity, and then velocity from 20 to 25.
So you
And I
did
could either
this
take-
one?
Yeah. So
And
I could
then-
probably either take the average of that, or I could just take the points at, I think, 15 to 25 to find the
Which is cool. So you took this one and this slope and averaged it with that slope?
Yeah.
Oh, that's a cool plan. That could also work. What did you get with that plan?
Well, I think it should be 5 feet, because I got 0 from 15 to 20 is the velocity.
Cool. Yeah, hold on. Let me write down some
Okay.
stuff here. So on this one from 15, oh, you just did 15 to 20.
sorry.
And then
Thank
20 to
you.
20 to 25.
Yeah.
That makes okay, that makes way more sense. It's cool. So you took that average velocity, and what did that turn out to
That's
be?
0, not moving.
It's a pretty much 0.
Yeah.
So 0
That is, yeah.
feet per second. Cool. And then what was this dude here?
That should be 10.
So negative 10?
Negative 10, sorry.
Negative 10, that's cool. Feet per second. And then you average those. I like that plan. And I think that might be exactly what we got if we did that slope there. I'm not sure.
So is it?
It isn't?
I don't.
3.
Let's check. what is this average here?
Oh, yeah, it should, right? 50 divided by 10, or, yeah.
Yeah, 50 divided by 10, yeah, so, yeah.
It should be -5.
-5 feet per second. Did I do this? Yeah, and that was
Yeah,
the
that's
same,
just that
same
Yeah.
thing, cool. So for this one here, we got -5 feet per second. Or if we took Hannah's approach of averaging these two and then dividing by 2, we get the -5 feet per second. Cool. Is that the true answer? So let's think about this. You're in your car. This is your car. You're driving. You got your foot on the pedal. You know damn good and well, because you've driven, everybody's driven, right? I just don't want to be presumptuous, but everybody's driven. Your needle does not stay solid, right? You're always trying, that's why we have to worry all the time. So you're always kind of gauging it, unless you have cruise control. But if your foot's on the pedal, that needle is always kind of fluctuating. So what they're getting at here is, what does the needle read at that instant? So right at this moment, what does the needle read? And this is where we'll get to what Katya was working with before, is we're going to need to figure out what is the velocity at an instant. And that's where we're going with this. What does that needle read right at that exact moment, because it's been wavering on either side of that. So I think these are great answers. And then what is our last one at 30 seconds? And so Mace, this was where you were like, what do we do here?
Yeah.
What did you do?
I didn't get that far, honestly.
That's cool.
I was more like trying to understand what we're doing for 20 seconds.
Yeah, fair enough. Yeah, there's a lot going on here. What could we do here?
Take the point of 30 and 100 feet per second, and then a point of 25 and 250.
Yeah, so it seems like the only thing we could do is maybe work with those 2 points. So Katya, this is a great place for me to check out that you can see we have a negative velocity here, but if I took just the vertical coordinate 100 and I divided it by the 30, it would be, I'd get 3.33, which doesn't make sense here because our velocity actually seems to be negative. We're actually going back. So does that make sense why we can't do that? Cool. Sorry to keep pointing on that, but I'm super glad you said it and thought it. So yeah, for this last one, probably the best we can do is find that distance change over that. So what is that? That's 250 minus 100. So let's see, delta D over delta T is negative 150, thank you, over 5.
Yep.
And so that is negative 30 feet per second.
All right.
Cool. Groovy. Every class is going to be loaded from here on out because there's so much to talk about. I want to start one little bit more so that you can at least make some more progress on your homework. We're going to take this idea of average velocity and make it a little more abstract in general and just talk about average rate of change for a function. So assume f of x is a function. So I've got an input and an output. This represents the formula for output given an input x. We've got a function, and let's just say, oh heck, it looks like that. So here's y equals f of x, here's x, and let's grab a couple points in here. So this point here is A, and this point here will be B. And we're going to make a definition that we're going to use for the rest of the semester. So the average change, average rate of change in f of x on the interval a to b. So the interval is always going to be the inputs. This represents the outputs. What's the average rate of change in the outputs given this input range? is equal to f, the value of f at the right end, so how high is that at the end, minus how high was that at the start, divided by the change in input. So we could actually write this a little bit more compactly, like this, using that delta notation, change in f over change in x. And so once we have a formula, this actually becomes just a matter of plugging stuff into formulas. Let's take a look at an example. In fact, let's grab one out of the book, because those are nice and all done for us. So if I've got y equals x squared, we'll start off with the chillest thing. This is actually problem 1 on page 77, but I'm going to add a little bit to it. So they're asking us a question: what is the slope of the line through the point 0.39? So let's get a graph. This is a good old parabola, like so. This is the y equals x squared output. This is the x input, and then we have 3, 9. So the question is one we actually can't even answer yet without calculus, but we can figure out roughly what it should be with the ideas we were just talking about. So what I'm looking for right here is, what is the slope of the line through a single point? So in some ways, what you were thinking, Katya, it was like very sophisticated, very advanced. It was like calculus. You're thinking at the instant, what is happening here? So right now, this will become super easy for us. This will actually become, I could look at this and tell you the answer is 6. And you'll be able to know that's 6 by just looking at this and doing a simple computation in your head. But what's that? You don't believe me?
No, never mind, I was just making a reference
To what?
3, 6, 9 triangles.
Oh, you thinking of some Tesla stuff or something?
No, just
Okay.
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 Triangles, I don't know.
I thought you were thinking some mystical things.
Yeah. My brain wanders.
That's cool. Hey, I'm with you. Also on TikTok, all the ADHD videos.
Oh, yeah, that's me.
Completely.
Yeah,
Yeah.
100%. It's weird. TikTok tells me too much about it.
It's a little disturbing.
Right? It's just like, I do that.
Yeah, I think like if you wanted to know about someone, you just go look at their feed.
Mhm.
And
Tells you all you need to know.
yeah, that's why you keep that away from anyone at all costs. So here's the plan we're going to do. We can't answer this exactly. So can't answer exactly, but we can approximate. And it was the idea I was talking about with grabbing some points nearby here and computing the average rate of change. So we can approximate by using 2 points near x equals 3 and finding the average rate of change. And so what we're going to do is actually, let's take the points. So let's do first attempt. Let's say x equals 3.1, so just a little bit to the right, and x equals 3. We'll just use the point itself. But now I can do an average. So let's crank this through. We're going to get, so our change in f over our change in x is going to equal, let's write this all out, f at the right minus f at the left over left input minus right input minus left input. We might need a calculator here because I don't know how to square 3.1, but this is actually 3.1 squared. I just plug that into the formula, minus 3 squared over, and then this one we can actually just simplify right off the bat. So could someone crank that through for us? I think the answer is 0.61.
That's exactly right.
Is that exactly right?
Yeah.
Okay, cool. I'll show you how I did that. That's like, I entertain myself sometimes up here trying to like do these things quickly. This is the difference of two squares. So this is actually 3.1 minus 3 times 3.1 plus 3. Right? Difference of two squares. X squared minus y squared over 0.1. This is just 0.1. This is 6.1. And a tenth of 6.1 is 0.61. So cool. I've entertained myself thoroughly for today. So it's 6.1. We don't really know what the units are. So the units here are mysterious because we don't really know in this context.
Wait, is it 6.1 before you divide by 0.1?
It was 6.1 before, yes. So it was 6.0.
Or I mean, yeah, 0.61.
Oh, wait. Was it 0.61 before I?
I got 0.61 on the top.
On the top, thank you, thank you. Oh, cool.
So that's 6.1.
Thank you. That's good. Yeah, because that's a super steep slope, right? Isn't it? And so then what is that? That is 6.1. There we go. Units are still mysterious. But that's the slope approximately of this line. What did I say it was exactly? 6. So that's pretty damn close. The goal here and the way we're gonna think, I'll get you out of here soon, Lorelai, I promise. No, it's cool. It's all good. No, you're great. It's like I'm just harassing you. The goal is to pick 2 points that get closer and closer and closer. This idea of getting infinitely close and arbitrarily close to something is calculus in a nutshell. And I want to show you how we can do this with Desmos. And so I put this Desmos app up in World Class. I'll just start this up. And you can use this to actually crank out some homework, or at least think about it or play with it. And we'll call it a day. We will probably need to talk a lot about the homework on Monday. I'm assuming so. So this is, if you go to content, and then, what, start without my data. Yes, stop wasting my time. No, just stop. What did they just reinstall Windows on this thing? For God's sakes. So Google, give me the Google, get me the hell out of here. So Desmos rate of change. I don't know, I'm gonna try to find the same one that I put up for y'all. This might be it.
Bang.
Dang, that's it. Cool. So, let's take a look here. What's cool about this app is it allows you to find the average rate of change between 2 points, and you can just grab the points and move them and look at what it gives you. Here's the average rate of change. It gives you f, the change in f over the change in x, and you can put your function in up here. So let's put in our buddy x squared.
It's pretty nifty.
It's pretty sweet. It's a lot of fun to mess with these things. So you just enter x, not negative x squared, positive x squared. And then I'm gonna make one of these points 3. And you can actually just enter the value if you want. And then pick a point that is, let's get out here. And it's, god damn, I love Desmos.
Me too.
It's so freaking nice. Okay, so there's 3.6. Now I can move this point in. Watch how the average slope changes. Right now it's 6.6. And notice how, get in here, you can't even see the line between those two. Where am I at right now? I'm not there yet. But there I'm at 3. I'm not even at 3.1 yet. There's 3.1. I'm at 6.1 as we computed. But as I get closer, notice how the closer I get, the closer that average rate of change gets to 6. And then when I get to 3, what's gonna happen? Uh-oh, why did it blow up? Well, damn, son of a bitch. All right, just gonna make that 3. There we go. Why is it barfing? What happened? Doesn't seem to like what we've done. What is the problem?
There's no slope, points are on each other.
The points are on each other. So if we have the same value for x1 and x2, on the bottom we've actually got 3 minus 3. We've got division by 0. So how in the heck are we going to do what I'm going to suggest here? We're going to take this f of x minus f of 3 over x minus 3, and we want to let x approach 3. How can we do that when this isn't defined even at 3? And this will be our first foray into calculus. That's right, raised eyebrow, perfect response. So, not yet. Start on the homework, please. This will be some of the more challenging work. Things will become more interesting and challenging, especially if it's been reviewed so far. Yay, see you all on Monday. Let me know if you have any issues or need anything.